On to the last section of Physics 20, which is waves. Good short introduction video on YouTube. Note that is not it. That is Beethoven's Fifth Piano Concerto, which is unbelievable. So go to this, physics, waves in general, minute physics. It's 3 minutes long and it's good. And then back to this. What properties of waves? And we'll just go. Well, of course, we know waves mostly as it pertains to water, but there are obviously many different types of waves, like sound waves, or if you have a rope and you jiggle the rope, then it's going to create a wave on that rope. And what should you know about waves? Well, first you should know that wave is just a way of transferring energy from one place to another. So when you speak, you are doing exactly that. Your voice is a longitudinal wave, or sound waves are longitudinal waves, and you're just transferring energy from your mouth to the ears of those people who are hearing you. And so on. Okay, and then we go into the characteristics of wave. So here's a wave, and we have these terms. Wavelength. A wavelength is the property that most people can spot easily and quickly. The wavelength is simply the length of one wave. And in this diagram, that is one wave. So that's a one wavelength. So the diagram, how many wavelengths are depicted in that diagram? 1, 2, 3. So in the diagram in your notes, you've got 3 wavelengths, and that is the symbol for a wavelength. It's lambda, the Greek symbol lambda, and it represents a wavelength, one wavelength. Then you get the highest parts of the wave are called crests, and the lowest parts are called troughs. Good so far? Moving on. Okay, we just discussed all that, the crests, the troughs, the lambda. Then we go on to, and now, so as I said in the last example, this was one wavelength. But the wavelength can be measured in multiple ways. As long as you go through that same distance, if I start here, then once I get to here, I have done one wavelength. Or if I start here, once I get to there, that is also one wavelength. So the wavelengths can be measured in different ways, but they are the same distance. Okay, and then we go to the concept of amplitude. And this will be more important when you get into math and the trigonometry. You don't need to know this right now, but in math 30-1 or 30-1, you will certainly need to know this y equals sine theta. This graph down here on your notes, and the amplitude here is 1, and the one down there is -1. That's basically a sine graph. And the amplitude is the distance from the equilibrium position. So this is our equilibrium position. We're again talking related to simple harmonic motion. And the crest or the trough. So just don't get confused with the amplitude and consider this to be the amplitude. That is incorrect. The amplitude is from the equilibrium position to a crest, or the equilibrium position to a trough. Okay, it's basically how big the wave is. So if you're a surfer, you want amplitudes, waves with big amplitudes. Okay, and so on. Moving on, and then we get wave diagrams, and this is a good analogy here. When you throw a rock into a lake, you see waves moving in a series of round ripples outwards. So they're called concentric circles, and they form a wave train. And this is how we best depict wave trains. The lines that we draw right here, and here, and all of them, they represent the crests, and everywhere in the middle represent the troughs. So the troughs aren't depicted, they're just invisible, the space between the crests. And then the wave just spreads out. Now, what happens to the size or the amplitude of the wave as it spreads out, we should probably instinctively know that as the wave moves out, the amplitude gets smaller. Why is that? Simply because the wave is now spread out over a much bigger circumference. So the energy of the wave is spread out over a much bigger circumference, and therefore the amplitude has to be small, right? Otherwise, if I threw a huge, massive boulder into the middle of the Atlantic Ocean from a helicopter, then it would create a tsunami and destroying half of the west side of Europe and the east side of the States and Canada. So the wave loses energy because it's spread out over a greater circumference. And then we show that the rays drawn in this diagram, the rays show the direction of the wave. Okay. And that is it. That's it for the introduction to the properties of waves. We'll go on to the next one in the next lesson.